end this short video series, perhaps appropriately with death.
Pander to me, kid. One tiny crack in the hull and our blood boils in 13 seconds. Solar flare might crop up, cook us in our seats. And wait till you're sitting pretty with a case of Andorian shingles. See if you're still so relaxed when your eyeballs are bleeding. Space is disease and danger wrapped in darkness and silence.
Based on the numbers, if you found yourself a character in one of these films, you're actually most likely to die in outer space from your ship exploding. But that's not really space killing you. People die in explosions, of course, all of the time right on solid ground. Some movies kill characters by making them float off into the void inside of their spacesuits. They either asphyxiate from too much carbon dioxide, or they just run out of oxygen, whichever happens first. Though we don't usually see the actual moment of death. In other movies, people get struck by debris. Large, zooming boulders are intuitively dangerous, but bits of rock no bigger than a grain of sand can be absolutely devastating because they're traveling at tens of thousands of kilometers per hour. If they don't hit you, they're still putting holes in the side of your spacecraft that, if left unchecked, will expose you and the rest of the travelers to the vacuum of space. Exposure to this vacuum is indeed how most of our characters, be they protagonists, antagonists, or hapless extras, meet their end. And it's usually by what we call explosive decompression, incredibly sudden exposure to vacuum, like flying through a hull breach or being shot out of an airlock. Horrors and thrillers especially enjoy using this to kill off characters. But no matter the genre, we usually don't see the characters die. They're simply flung out there somewhere and never seen again. Or they eventually come crashing into the hull of another ship for comedic effect. But for the few movies where we do witness exactly how the vacuum of space kills a character, well, Montgomery Scott sums it up quite nicely.
It is not going to be all right. You want me to open an airlock into space, whereupon I will freeze, die, and explode?
Let's look at each of those. We'll start with the less representative of the fates. Exploding stems from the fact that the lower the atmospheric pressure, the lower the boiling point of water. So in a zero pressure environment like space, all of the water in your body should instantly turn into a vapor and therefore rip you to pieces. But in reality, your body's own internal pressure would keep a lot of the water from boiling. It is true, though, that some would vaporize. You would swell up as a result, maybe up to twice your original volume. Tiny blood vessels like the ones in your eyes might even burst. But your various tissues are both stretchy enough and strong enough to hold you together. We measure how hot or cold something is by how fast its particles are moving. The slower the particles, the colder it is. If the particles literally aren't moving at all, even at the subatomic level, that would be the temperature of absolute zero. A true vacuum can't have a temperature because there's no particles to measure. But space isn't a true vacuum, it's full of, among many other things, photons left over from the Big Bang. Those photons don't have temperatures either, but they do have energy that they can transfer to any particles that they hit. That energy is equivalent to 2.7 degrees above absolute zero. And that is cold. But for matter in space that can have a temperature, be it a star, or a human, or a speck of dust, it can only transfer heat through the vacuum by radiating light. You're doing it right now, in fact. That's what thermal cameras detect. But it's not a quick way to get heat out of a human body. Empty space literally insulates you against everything else in the universe. Kind of like a giant thermos. It's fairly rare in any of the reviewed genres, but characters exposed to the vacuum of space do occasionally survive. Some have an easier time of it though, especially depending on the genre.
Space, says the introduction to the Hitchhiker's Guide, is big. Really big. You just won't believe how vastly, hugely, mind-bogglingly big it is, and so on. It also says that if you hold a lung full of air, you can survive in the total vacuum of space for about 30 seconds.
If a movie wanted to accurately represent survival, its characters would need to be aware of a couple of things. First, once someone has undergone explosive decompression, all of the air in their lungs and digestive tract is going to force itself out of their body, attempting to balance the concentration of air inside and outside of them. Despite what Stephen Fry's voice just told us, they should under no circumstances hold their breath. Their lungs will rupture, and the air will likely get injected into their bloodstream and travel to their organs like their heart and their brain, killing them. What should they do instead?
Exhale.
You gotta be kidding.
Exhale!
Oh, no, no, no!
Second, the character is going to lose consciousness in about 10 to 15 seconds because their brain no longer has a supply of oxygen. That's how space kills a person, not insta-freezing or exploding, a simple lack of oxygen. Some films will fudge this number so lone protagonists can save themselves, but in reality, if you had a buddy to come rescue you, you could survive exposure to the vacuum of space for up to 90 seconds. But that doesn't mean that you would be home free after that, as movies are quick to remind us one's death might come at the hand of a more exciting force. Like getting the worst sunburn of your life. Or surfing. Surfing into a planet's atmosphere. One thing that they never address is a character dying from cancer decades after being exposed to months of ionizing radiation during their journey. But just like these stories, we simply don't have the time to cover it. Thank you so much for taking the time to watch this short series. Or at least this one video in the series. There are obviously a lot of topics that I didn't have the time to get to. Extraterrestrial life, extrasolar planets, hydrostatic equilibrium and its relationship to the life cycle of stars. If you've finished watching all of the videos you intend to, please help me complete my dissertation by clicking on the link below to fill out a very short anonymous survey. If you have any questions, you can direct them to my Twitter account, @SciCommJess, and feel free to share this project so that I can get more data to analyze.